In this tutorial, we learn how to create a geometry of pipe flow using ICEM CFD. Then we will do meshing in ICEM CFD, followed by simulation in ANSYS FLUENT. This is the duct which has 4-inch height at the inlet and 6-inch height at the outlet. In order to get uniform flow, here we have put 3 baffles. This baffle 1, 2, 3. These baffles are used to get uniform flow through pipe, because we know in pipe there is a non-uniform flow because more flow rate is at the center and less at the outlet. We want to see that flow rate to be the uniform through this 6-inch outlet pipe. Once we understand the geometry, then start creating the geometry in ICEM CFD. This is ICEM CFD. First, you have to create geometry using point option, line option, surface option, then blocking. Click here, then create the first point. First point is 0. That means this point is visible here. The next point, as per geometry, is 0 at 4. And these 4 points are created. Please note that we are taking in neutral dimension, because this we are taking in inch. Whatever you give dimension, accordingly geometry will be created in ICEM CFD. Then you have to feed into the machine, and then go to the simulation. The simulation in the FLUENT. In FLUENT, you have to convert an inch into the meter. That will be done in CFD solver. Then next, you have to create a point at 4, and this is 0. This point you have to create. Then you have to also create other point, that's 4, 4. Then they create point, the first point, then this is again point, then this point. This means we have created this point 4. Then we have to create this line. Then this point we can create. Then this gap is a 6 inch. This is a 3. Then we can take 1 point. This is y is a minus 1. This is a 6 and this is a 10. Then we have created this point. Then minus 1 point, then at a 0, then this point will be created. Just you can delete this one delete. You can create a point y1. Sorry, go back. This is -1. Then create that point as 0.5. Then again this is at 2. So this is as 3.5. Then this create as a 0.5. Then create this as 12 point. Just take far away. You can take this as a 14. That means we have created a point. Then -1. This way we have created all the required point. Click here, select this line, this line. Select this one, this one. Select this one, this one. Select this one, this one. That means first we created this point. These points are created initially. First is created the point. The second step is you have to join the point with the line. Use this line command to connect this line, connect this curve. Then create this line. This line L1, L2, this one, this two. Create all the required lines. Then create this surface. The third step is create a surface using two curve method. Using two curve method. Here is the option is the select using the two curve method. This is two curve method. We can use it. Just select this one using this option. Click here. Select this first curve, second curve using the left mouse button. Using left mouse button. And then use middle button. Then middle mouse button. Because selection options are also there in here setting. If you want to change anything, then here options are also there. Like selection. Then here option is there. Selection. Now here is a setting. Here solver. See this is the selection options are there. You can use left mouse for rotate, middle for pan, right for zoom. This is for rotate. It's better to put middle button for the zoom. And you can select this option. You can use left option for the selection and middle for OK or acceptance, and the scrolling we can use for the zooming also. Here we can create a surface. Select this curve and this curve. Curve will be created here. See, this curve will be created here. Select this one, curve will be created. After that, we can save the project. We can save anywhere. You can use you can put the duct baffle. So many files are created. It's better to save in the in separate folder. The next step is you have to create a name. Because I want to select only line. Because select this line and give as a this is as the inlet. The inlet will be reflected here. This is as outlet. Then middle click, then it will be created. And this is the baffle. Using this option, click create part middle one. Using this option, you can hide the surface to select the curve. Select using left mouse, middle click. Here put as a wall baffle. These baffles are created. Once we know inlet outlet is fine. This will be wall. This will be wall definitely. The next option is the blocking. Here select the 2D planar because this geometry is 2D, hence select here 2D planar because 2D block will be created. Once then after that 2D block will be created, then you have to associate here. Once 2D block is created, the next step is association. Next step is association. Say this way block is created, then you have to split the block. This block is splitted here. Here I am also splitting the block at this point. The next step is association. In association, you can use this option. What is this option? This option is associate this edge with this curve. If I hide this curve, then you can see this yellow color. That means these edges are associated. Black means default association, and this is the internal face. This is not associated. That means this is not associated. But other thing is that these are blocks are there. But you have to also again split here. You can split this block here. We can split here. You can split this point. That means we can create a structure mesh. And then again we have to oscillate here. Then again this slate here. That means naming has been created. That means one block is you have to associate. See, that means all blocks are associated. That means one surface element. And here put here option is there, is show association. And here you can see all edges are associated. This is also associated. This is also associated. This is associated. This all the walls should be associated. See, all BC should be associated with the curve. Once association is over, the next is sizing. I can select this one, 10. You can select 10 or 20, whatever you want. Here also you can select 20. Select 20. This is also 20. This is also, you can select as the 30. You can select the graph option is also there. You can select the more fine near the wall. That option you can select. This option you can select. You give near the copy parameter. You can use a 14. This we can use as a here also 14. You can use as a 40 here. And save the file. You can show pre-mesh information. Here pre-mesh information is that means 8892 element will be created. 8892 cells will be created. That is the predictor before the computation. Click here, compute, convert to the unstructured mesh. This way mesh is created. But if you want to more fun here, you can use option linear. That means more fun will be here. Yes, see, this is a node will be created. Then again recompute, convert to unstructured mesh, replace. See, this is good quality mesh is created. This will be hex elements are created. This is the inlet and this is the outlet, and here baffles are there here. The next step is here we can add mesh. Here in block we can show the block face. We can show it in color. The next step is we can select the element parts here. We can select this one. This is as a fluid one. because this I can also add to this part. And this create a part. This is a fluid too, because why I creating here? Because this why I created this separate fluid here, because this is a fluid is one is there, this is a fluid one and this is fluid two. Because if we don't give the separate name, then this wall will be merged in fluent. This wall will be merged in fluent, because then this baffle will not see. Hence, is always better to give separate name here and separate name here fluid, so that this wall will not be merged and fluent will understand there is a wall is there. To consider it, you have to consider separate fluid zone around the one wall. That means one wall should be separated by two fluid here. Let's save it. Recompute, convert to unstructured mesh, replace. Then you can see this mesh. Every mesh is created. Then first save it. ANSYS FLUENT. Boundary condition we have already given. Okay, click yes, Hex. And here we are using 2D mesh. Here you can write 2D duct flow. You have to select here 2D option. And this is the file name. This will be 2D duct flow at the dot msh. Means dot msh will be here. This dot msh will be here after saving this file. Then save it. Uh, that means file will be saved here. Then also save the project. Then you can select the FLUENT. It's a 2D duct. Give the file path. Then start. Then file, read mesh, this 2D mesh, read it. That means it is not supporting. That means this F1 is started at some issue is there. Read mesh file, 2D mesh file. There some issue is there. After creation of geometry and meshing in ICEM CFD, you have to import mesh file, and then check the size. It has around 10,412 cells. You can go here, display, all ages, and then see. This is the mesh. This is a very good quality mesh. Then check the name. This is the inlet. There are two out. There is a one outlet, and you have to check the wall faces properly. This is the geometry base. That means this should be internal. And check what are other faces. This is wall back. When these are the outside wall. And these are three are the baffle. This is the inlet and outlet. That means geometry is okay for the simulation. Go to inlet here, define velocity inlet as 3 meter per second. Don't forget to do order setting, a scale, because I have created geometry in the inch, because I have created this geometry inch. And this total length is 14 inch. If we convert into the meter, then it will be is equal to a scaling factor multiply into the this length in the inch, and then scale it. That means all dimensions have been changed. And then select the turbulence model, case plug model, and realizable model. It can consider recirculation. Click here. I think next step is material selection. Here air is selected as a material. Please note Reynolds number for this flow is equal to is the characteristic length into the density here into the velocity inlet. Whatever you velocity here in that inlet velocity, that means rho into characteristic length divided by this dynamic viscosity. That is equal to Reynolds number. For this flow, we can calculate the characteristic length, and definitely flow is greater than critical Reynolds number. That means flow is a turbulent flow. Close it, change it, and close. Then go to boundary condition. Inlet is defined as velocity inlet, 3 meter per second. Intensity you can give as average value, and outlet you can select outlet vent. You can take -5 Pascal. And then control I take simple solver. You can change the relaxation factor if you know well about the simulation for faster conversion. Then after that, initialize, then residual, then residual keep it below 10 to the power minus 6 for all the variable. Okay, go calculation activities, auto save after 500 iteration, make maximum 2 cases and the write case file. Uh, because this has very good mesh quality, you can see the mesh quality is good. That means it has 0.9865 is a orthogonal quality. That means very good mesh quality. That means convergence will be better. Then click here, give some 6000 iteration and run it. Here floating point error is occurred. That means some issue is there. We can select the simple algorithm. The momentum it should be here 0.3 or 0.4. That was a mistake. Initialize and then run the simulation. See convergence is converging much faster. That means it is converging better way. This continued equation, this xy velocity, y velocity, k and is plan. And check the contour. Check the fluid run and see the contour. You may surprise flow is not going here. That means something went wrong. This should be as interior. Then run the simulation. Then stop the simulation. Check the contour. That means flow is going properly. Also check the flux balance. That means flux balance is 0. See, this is the flux balance. This is net mass balance is 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 around 10 to the power minus 6. That means it is close to 0. That means fluxes are well converged. That means fluxes between inlet and outlet, which are the well converged. You can run If you want to check it, press Ctrl C and check the control. See this, it is flowing properly. Let it run for further simulation, for further number of iterations. We can stop, check it. See, here is the flow rate. You can control the velocity magnitude like 3.5. So you can see where is the non-uniformity. That means high velocity is here and low is here. You can check 6 here. You can understand. You can run for further iteration to make this solution. This solution should be consistent. As it passes through the number of iteration, this solution should be consistent. Check the convergence whether it is going below 10 to minus 6 for this all this variable. Check here. And check the contour. And then you can save the case data file. This way we learn all these things. We can also check the pressure control. Whenever there is a difference in pressure, that means there is always difference in velocity. Means by controlling this pressure gradient, we can control the amount of the mass fluid passing through the each pass. This way we learn how to optimize duct. If this configuration is not okay, then you can try by changing this configuration. You may take some longer duct in geometry, then mesh, then simulate it and check which has lowest distribution of velocity across the section. Thank you for attending this lecture and tutorial.
Thank you for attending this lecture. For more information about CFD analysis of any problem using ANSYS FLUENT and OpenFOAM, you can visit website www.com CFD Flow Engineering. It covers most of the important topic for engineers, scientists related to the CFD and flow engineering, and also covers topic for flow technology. Thank you for attending this lecture. God bless you.